Okay, so now again, when we have a particular input sentence we're trying to translate, we're going to define the idea of a derivation, which is basically just a sequence of phrases drawn from the set P. Okay, so a derivation is just a sequence of phrases, P1, P2, up to P capital L, where L can be any positive integer. Okay, so these sequences can be any length. On the next slide, we'll talk about constraints on these derivations, which make them valid or invalid. So here's one example derivation. So this is saying, to translate the example that I just shown you, we can choose firstly a phrase which says that we translate words 1 through 3 as we must also. Next a phrase translating words 7 through 7 inclusive as take. Then we have 4, 5 as this criticism, and 6, 6 as seriously. Okay, so a derivation is just going to be a sequence of phrases. And these phrases are going to define a translation in the obvious way. So I'm going to use E of Y just to pull out the English string, the translation underlying this particular example, and that's taken just by concatenating these English strings. So we must also, followed by take, followed by this criticism, followed by seriously. Okay. So in short, a derivation is just a sequence of phrases where each phrase is again an STE triple. S is a start point, T is a end point, E is an English sequence of words. So let's now look at what makes a valid derivation for an input sentence that we're trying to translate. So for any input sentence x, which consists of n words, x1 through xn, I'm going to use y of x to refer to the set of valid derivations for that sentence. So this slide is going to give the abstract definition. On the next slide, I'll give an example illustrating these ideas. So y of x is going to be the set of all finite length sequences of phrases, so P1, P2, up to PL, where L can be any length, where we satisfy the following constraint. So firstly, we say that each phrase, remember each phrase is a triple ST, and then E, which is a sequence of English words. So each of these phrases has to be a member of the set of phrases for x1 through xn. So each phrase has to be valid under the phrase-based lexicon. The second constraint is kind of obvious. It just says that each word in the input sentence has to be translated exactly once. And the third case is a little more interesting. So again, this is an abstract definition. We'll give an example on the next slide illustrating it in some detail. But phrase-based systems make use of something called a distortion limit. And this is going to be a hard constraint on how far phrases can move. So a typical value might be little d equals 4. This is the distortion limit. And what this is basically saying, remember T of pk is the end point of the kth phrase, and S of pk plus 1 is the start point of the next phrase. Okay, so we might have a sequence of two phrases, we must, and then we might have 3, 3 also or something. And we're going to look at this endpoint, that's T of pk, and this start point, and make sure that those two values aren't too far from each other. So we're going to have a hard constraint over how far phrases can move. And so this is taking the absolute value of T of pk plus 1 minus S of pk. So in this case it would be the absolute value of 2 plus 1 minus 3, and this is equal to 0 in this case, so this distortion would be 0, which is less than or equal to 4, and so we've satisfied the distortion limit. Okay, so intuitively these two phrases are right adjacent to each other. I've translated first words 1 and 2, and then words 3 and 3, and 3 is adjacent to 2, and so the distortion for this particular pair of phrases is 0, and that satisfies the distortion limit. In addition, we have a constraint at the start of the sentence saying the start of the first phrase, or 1 minus the start of the first phrase, has to be less than or equal to d. Okay, so we'll come to this an example of this in a moment. The reason for this distortion limit is really twofold. Firstly, it's going to reduce the search space of possible translations. and that will make translation more efficient. And second, empirically, it's been found that having a distortion limit of this form can very often improve translation performance, because if these phrases are moving too far, the translations tend to be rather poor. The flip side of that is that this is really an incredibly crude way to control reordering between different languages. Different languages have different word orders, and we're simply imposing a limit, saying we're only allowing two languages to vary in word order by this hard limit, d equals 4. At the very end of this lecture, I'll talk about more recent methods or alternative approaches that try to build more sophisticated models of this reordering effect. Okay, so let's illustrate these definitions with an example. I'm going to show you some different possible derivations for this example sentence, and we're going to check if they're valid or invalid. So here's a first possible derivation. So we first, intuitively, we first translate wir müssen auch as we must also. And secondly, let's number these words, 1, 2, 3, 4, 5, 6, 7. The second phrase says let's translate words 7 to 7 inclusive. That's this single word nehmen. And we'll translate that as the word take. And then we translate words 4 and 5 as this criticism. And finally, we translate word 6 as seriously. Okay, so this is our final translation, which is actually a pretty good translation of this German input. We must also take this criticism seriously, and it's been produced through this derivation, this sequence of phrases. So this is actually a valid derivation, and we can check that. So one we need to check is each word translated once, or exactly once. That's the first thing we need to check. Okay, and if we look, we can see that, sure enough, every one of these words is translated exactly once, and so we satisfy that constraint. The second constraint is the distortion limit. And so that's a little bit more complicated. Let me go into that in some detail. So we're going to assume that the distortion limit d is equal to 4, and this is how it goes. So I'm going to check the end point of each phrase and the start point of the next phrase, so 3 and 7, and I'm going to calculate the value for 3 plus 1 minus 7. If you remember, what we wanted was t, the magnitude of t of pk plus 1 minus s of pk plus 1 is less than or equal to d, where pk is the kth phrase, pk plus 1 is the k plus 1th phrase, t is the end point of a phrase, s is the start point of a phrase. So if I compare 3 and 7, I calculate this. This is equal to, this is the absolute magnitude, this is the absolute magnitude of 3 plus 1 is 4, minus 7 is minus 3, which is equal to 3, and that's less than or equal to 4, okay? So these two phrases are essentially close enough to each other. That's what this is saying. We go through term by term. So next I compare 7 to position 4, again taking the end point of this phrase and the start point of the next phrase. And I look at 7 plus 1 minus 4, and then it's actually equal to 4, which is less than or equal to 4, so good. That's also valid. Next one I check is 5 followed by 6, the end point of this phrase, the start point of this phrase. So I look at 5 plus 1 minus 6. This is actually the magnitude of 0, which is clearly less than or equal to 4. It's 0 because these two phrases actually are consecutive in the sentence. So 4, 5, and 6 are consecutive. And then finally, I look at this very first position. So remember, I also had magnitude of 1 minus s of p1 is less than or equal to d. So I have 1 minus the start point of the first phrase is just 1. So this is magnitude of 0 is less than or equal to 4. Okay, so in short, this derivation satisfies, firstly, this constraint that each word is translated exactly once, and second, that none of these phrases move too far, that the distortion limit is satisfied. Okay, and the distortion limit is calculated by looking at the end point of each phrase and the start point of the next phrase and making sure they're not too far from each other. Okay, so here's a second derivation, which we'll see we can rule out very quickly as being invalid. And so again, this is a sequence of phrases where each phrase consists of a start point, an end point, and a sequence of English words. The problem with this, of course, is that these two words have been translated twice. So let's just give a count of how many times I've translated each word. I think word 3 is once, 4 and 5 is once, 6 is once, and 7 is 0 times. And so we've clearly, this is a failed derivation. This is not a good derivation because it doesn't satisfy the constraint that each word is translated exactly once. Here's a final example. And so we'll again check the two constraints with this particular derivation. So the first constraint is, exactly once. It's each word translated exactly once. And in this particular case, you can see that that's the case. If you look at these phrases, every word is translated exactly once in this example. And then the second question is, what about the distortion limit? And so let's go through using the procedure I just showed you to check this. So firstly, let's compare 2 and 7. And again, I'm going to assume that d, the distortion limit, is equal to 4. So 2 and 7, so I take the magnitude of 2 plus 1 minus 7, which is the magnitude of 3, so minus 4, is less than or equal to d, and so that's fine. So this first pair of phrases satisfy the distortion limit. Let's look at the second pair, though. So here I compare 7 to 3. And here I have 7 plus 1 minus 3, this magnitude. This is 5. And is that less than or equal to d? No. So we've immediately seen that this pair of phrases have violated this distortion limit. There's too much of a distance between position 7 and position 3 under this definition. So this is actually an invalid derivation. So in spite of satisfying the constraint that each word is translated exactly once, we violate the distortion limit, and this is ruled out.